Bismillah ar-Rahim. Today we are going to talk about bubble T and UT calculations using Raoult's law. And the agenda for this talk is based solely on the difficulty of using bubble T and DUT calculations compared to bubble B and P calculations. And we are going to talk about two approaches to tackle such a problem. The first one is brute force solution of bubble T and UT, and the other one is bubble T and UT calculations as a systematic algorithm. And for example, if you would like to program them or use them in a numerical method, and some examples about this. The difficulty of bubble T and UT calculations is that we do not know temperature. Temperature is not known. Therefore, vapor pressure is not known a priori. So if vapor pressure is not known a priori, then vapor pressure, as we know, is a nonlinear function of T. For example, consider the Antoine equation, which is a simple vapor pressure model. It's clearly that the vapor pressure itself is an exponential of the temperature, which makes it difficult to evaluate when we have summations of those terms. For example, in the brute force solution of bubble T and UT, we formulate the calculations as the total pressure for both. In this case, if we look at a binary system, for example, in bubble T calculation, the total pressure is X1 P1 vapor plus X2 P2 vapor. And what we know is the total pressure is known, the mole fractions in the liquid phase are known, and the parameters for each components are known for the Antoine equation. So the only unknown in this equation is temperature. So this is a single nonlinear equation with a single unknown, which is the temperature. We can use any numerical method to solve for this, whether for bubble T or UT. The expression for the binary system for the DUT is that the total pressure is the summation of the reciprocals of mole fractions in the vapor phase divided by the vapor pressures. To demonstrate this, I'm going to show you an Excel worksheet for the same example that we were talking about previously in the bubble B and DUP calculations. I'm just flipping the variables. So instead of knowing the pressure, right now I will assume that I know the temperature, I know the pressure, and I don't know the temperature. So the total pressure is 0.07145 bars, and the temperature is unknown. If you recall the example in the previous lecture, the temperature should be 300 Kelvin. That yielded 0.07145 bars. So to formulate this equation, we have three components. So in the three components, we have the total pressure, since it's a bubble T calculation, is the summation of Xi Pi vapor, and formulated using the Antoine equation, it yields this equation. And clearly we cannot separate T on one side and everything else on the other side. So I'm going to use Excel solver to solve for this. The first thing is browse. I need this file, which is this calculation. We have given total pressure is 0.07145. What I'm going to do using Excel solver is really to convert the problem into a minimization problem or a root finding problem using Excel's solver. So we have the mole fraction in the liquid phase, 0.4, 0.3, 0.3, and we can obtain the Antoine constants from the thermosolver. And what we need to do first is to assume a temperature. So I'm going to use, for example, 290 degrees Kelvin. We know that the correct answer should be 300 Kelvin. But right now, it's an initial guess. I don't know it a priori, really, because we have solved this example before, we know it's 300, but we don't have this luxury usually in many other situations. So I'm going to use an assumed T of 290 Kelvin. It's just an initial guess, it's not the final answer, so don't worry. What I need to do right now is to calculate. I will assume that I have the temperature and I don't have the pressure. So I'm flipping the type of calculation from bubble T into bubble P calculation using this assumed temperature, which is the initial guess of temperature. So I'm going to calculate a total pressure using bubble P calculation, which we mentioned that it does not need really trial and error or iterative solution. At this assumed temperature, we have a calculated total pressure of 0.04377, but we know that the real value is 0.07145, which clearly shows that this initial guess is not the real initial guess, the real solution. So what we can do is really use a hit and miss thing. For example, I can use 320. In this case, I can notice that increasing the temperature will increase the total pressure, but above the value we would like to have, 310, it is still above 295. It is now below, so I know I'm bracketing the solution between 295 and 310. I can carry on. I'm sorry. Two. So I know it's between 299 and 300. But if you notice, this is a hit and miss solution, and nothing really can tell you that you are approaching the solution quickly. What I'm going to do right now is to go to Excel Solver. In Excel Solver, you can find it in the Data tab, and you have the solver. Many times in Excel, if you don't see the solver here, usually you need to go to the options and enable it from the add-ins, Excel add-ins. So the solver, what is the solver? It is a small add-in in Excel that can solve your an equation for you, whether you want the minimum of that function or its maximum, or a value of certain value, not really zero. What I'm requiring it right now is to have a value of 0. What is the value of 0? Let's go back here to the basics and find this cell. What is this cell? It is the P calculated minus P given. Ideally, this value should be 0. If our temperature, assumed temperature, is the correct temperature, then the total pressure that we get from the calculation is the same as the total pressure we know from the problem statement. But right now, we see that this value is not really 0 from a numerical point of view. So in solver, what I need to do is set objective. My objective right now is to set the difference between the calculated pressure and the given pressure to a value of 0. You can set it to any value if you have other situations, or you can ask Excel to minimize or maximize such a function. Now, how is this value to achieve the value of 0? The temperature should be varied in such a way to force this value to be a 0. So I'm going to tell it that the cell of assumed temperature is the value to be changed to force the target or the objective function to be a 0, and don't worry about the other things. I will tell Excel to solve, and I will tell it keep the solution. And now voila, if you notice the assumed T in Kelvin, 299.9998, which is practically 300 Kelvin. So Excel found us the solution. For example, if we started from an initial guess of 250, notice now the objective function is not a 0 once again, but if I can go to solver and tell it to solve it once again, Excel is now getting the right answer for this kind of solution. And the same thing happens for dew point temperature calculations. What we need to do right now is just to define the function and calculate the value of yi over pi instead of XIPI and carry out the calculations. For example, in the dew point temperature, let us set it to 350 Kelvin and tell him that solver solve, and once again 299.998, practically it's 300 degrees Kelvin, which is the value we know we should get. So this is brute force, and Excel is using a numerical method in this case, definitely, to evaluate this function. Now, what if we would like to have a hand calculation for this value, or we want to program our own dew point temperature and bubble point temperature calculations? In bubble point temperature and bubble point and dew point calculations, what we need to do is an iterative solution, an iterative kind of solution. For example, in bubble T, what we know is the pressure and the mole fraction is the liquid phase. And we know the components, so we can get the Antoine constants for those components. The idea right now is to get a good initial guess. A good initial guess is critical in either finding a solution or minimizing your workload. That is, to minimize the number of iterations that you carry out. So we will use a heuristic. What is a heuristic? We use an initial guess calculated from our knowledge of Raoult's law behavior. In Raoult's law behavior, we know that the bubble temperature should never exceed the maximum boiling temperature at the given pressure for each component, and should never be below the minimum temperature of the lowest boiling component in our case. So what we are going to evaluate now, I'm inverting in this stage Antoine's equation to put the temperature on one side and the total pressure on the other side. I'm using the given total pressure, which is known total pressure, and each component. So I'm calculating essentially the boiling temperature of each component in the system at the given pressure. Now we have for each component, but what happens if we have a mixture? What happens if we have a mixture? We can think according to the concept that most likely the component with the highest concentration will drive the system boiling temperature or bubble temperature to its side. So we are using an initial guess that will be weighted by the mole fraction of each component. We have the excess, we have the T saturation, and so we assume that the initial guess is nothing but the weighted average of the boiling temperatures of those components at the given pressure. Now we have an initial guess of temperature, so we flip our calculations into a bubble B calculation at this T0. So we calculate a new pressure. It is not the actual pressure, but it is a new estimate for the pressure using bubble point calculations at the calculated initial guess of temperature T0. From this, we calculated the mole fractions in the vapor phase using Xi Pi vapor over the actual P. It's not the estimate P, it's not P0. It's the actual P. Why is that? If we divide by P0, we will always get a summation of Yi equals 1, which would not help us in solving iteratively. But if we divide by the actual pressure, we will get values different than 1. Whether above or below it, that's a different story, but it is different than 1. So we check now if its assumed initial guess of temperature is actually correct. It should yield a summation of Yi's equal to 1. But as you might know that the computer, we cannot use integers or exact 0, so we use a tolerance. So we will accept that if 1 minus summation Yi and the absolute value is less than 0.0001, 1 in 10,000. You might think that, why is that? No, there is no justification other than you have to set a criteria for convergence. If you would like to set it 1 in 100,000, it's okay. 1 in a million, it's okay. But usually, if you go to the lab, Usually with our best apparatus, we cannot get better than this resolution or uncertainty in mole fractions. So it's okay for me to have 1 in 10,000. Now, if the assumed t yielded the summation, this different, less than 1001, then it should be the actual T or the bubble point temperature. So we will output T, accept T as T0. Now what happens if this difference is greater than 1001? We need to correct ourselves that the initial guess is not the correct value. How do we correct this systematically? What I'm going to use is something I will call key component. What is a key component? You can use it arbitrarily. In this case, I'm using the first component. You can use number 2, you can use number 3 or number 1000. Regardless of the number of components in the system, it's much more convenient to use the first component and go on with the solution. So I'm using the first key component as the key component as the first component. So what I'm doing right now, once I used the key component, is to correct the vapor pressure using this equation. What does it say? That the vapor pressure of this component is to be corrected by dividing the vapor pressure at the initial guess T0 by the summation of Yi. Now imagine if the summation of Yi is greater than 1. What does it mean? That the temperature is much higher than required. So what I'm doing right now, if summation Yi is greater than 1, I'm reducing the vapor pressure. And if I reduce vapor pressure and recalculate the boiling temperature of this component or the vapor pressure of this component, then definitely the temperature will be reduced. Now imagine if the summation of Yi is less than 1. If it is less than 1, it implies that the assumed temperature is less than the actual temperature, so we need to raise it. How do we raise it? If we divide P1 vapor by a fraction that is less than 1, it will be increased. And if it increased here, we can go back to this equation and substitute instead of P, the P1 vapor. So we can find a new initial guess for T, then we can calculate the bubble point pressure, the new bubble point pressure, calculate Yi's, calculate summation Yi's and its difference from 1, and till this cycle converges, we can go on doing this. The same thing for bubble duty calculation. In duty calculation, what we are doing really is the same as bubble T calculation, except that once we have the initial guess of temperature, we are calculating a due pressure calculations. Then we are calculating the mole fractions in the liquid phase using the total pressure that is real total pressure. So what I'm going to do is use the real vapor pressure, which necessarily, if the assumed temperature is not the correct temperature, should yield values of xi, the summation of xi, different than 1. And in this case, for example, we need to go and correct ourselves. Now, the major difference between bubble T and UT calculation is in the way we correct ourselves. In the way we correct ourselves in the DUT calculation, we multiply the vapor pressure by the summation xi. Why is that? Now consider the same situation. If summation xi is greater than 1, what does it mean? It means that the temperature is much less than what is required. So I need to raise the vapor pressure and correct the initial guess of temperature here. So what I need to do is to multiply the vapor pressure by the summation of xi. The same thing if we have a larger value of initial guess of temperature. It will yield smaller values of xi. The summation is less than 1, so I need to reduce it, and reducing it by scaling the vapor pressure, then recalculating the initial guess of temperature and going on like this. To demonstrate those concepts, consider the same examples, and I will solve it using Excel in 3 or 4 iterations. The same example, for example, in bubble T solution, just waiting for Excel to open. What we have right now, or what is given, is the total pressure and the mole fractions in the liquid phase. What I'm going to do is to calculate the boiling temperature for the given pressure using Antoine equation. That is the inverted Antoine equation. I'm going to put the T on one side and everything else on the other side. For example, if we notice at a total pressure of 0.07145, the boiling temperature of benzene is 260 Kelvin. For that of toluene 311, and for metaxylene it is 334.986 kelvins. Now, due to Raoult's law being a scaling law, we know that the bubble temperature should never be below 286 or above 334 degrees Kelvin. So I'm going to use an initial guess. What is a good initial guess? As long as you know that the bubble temperature lies between 206 and 335 degrees Kelvin, you can use any initial guess. But usually, weighting the temperatures by the mole fractions will give you a good initial guess that will minimize your effort in the number of iterations that you can carry out. For example, using XITI 0.4 times 286 plus 0.3 times 311 plus 0.3 times 334 should yield a T estimate of 308 kelvins. This is what I'm going to use as a bubble B calculation. A bubble B calculation I'm going to use right now at this temperature. I'm going to calculate the vapor pressure of benzene, toluene, and xylene using Antoine equation as is. It's not the inverted Antoine equation right now. I'm going to use the Antoine equation as is. So I have calculated it. I have calculated xi pi star. Then I will calculate yi. But notice what I'm going to do. I'm not going to divide by the pressure calculated here. I'm going to divide by the pressure that is given, that is known here. So if we notice right now, what is the summation of those yi's? It's 1.46. 1.46 is much higher than what is required. We require the summation of yi to be 1. If the assumed temperature is correct, the summation of yi should be 1. So what we need to do right now is to scale down the vapor pressure. And as I mentioned before, I will use benzene as my key component. I know the vapor pressure of benzene is 0.1991 and the total mole fraction summation of mole fractions in the vapor phase 1.46. What I will do is divide the vapor pressure by the summation of mole fractions in the vapor phase. It will yield a vapor pressure of 0.1363. Now, this vapor pressure, I'm going to use the inverted Antoine equation. What do I mean by the inverted Antoine equation? I will put temperature on one side and everything else on the other side to calculate the boiling temperature or the temperature equivalent to this vapor pressure for benzene. It yielded 299.711 Kelvin. This is my new initial guess for temperature. What I will do right now is, once again, all this table is fixed. I'm going to calculate the vapor pressure of benzene already is calculated. Calculate the vapor pressure of toluene on at 299.711 and xylene at 299.711. Then calculate the xi pi star and yi, taking care that we are dividing by the actual pressure. Now notice what happened, that we dropped from 1.46 as a summation of mole fractions into 2.986, which is very close to 1. But it's not as close as we would like it to be. And remember that we would like it to be within 1 in 10,000 of ionity. So we need to carry out another iteration. How do we carry out another iteration? Once again, our key component is benzene. Its vapor pressure right now is 0.1363 and the summation of mole fractions in the vapor phase is 0.986, which necessarily means that our temperature is lower than required. So I need to increase the temperature. How do I increase it? I will divide 0.1363 by 0.9864, which should yield 0.13817. Now I have this vapor pressure of benzene. I will calculate the inverted Antoine equation, and it should yield an initial guess of temperature of 300.01. Same bubble B calculation, and summation right now is 1.00048. It's most satisfactory, but once again, if we would like to have it within 1 in 10,000, we still need to carry out more iterations, correct the Weber pressure of the key component by dividing the Weber pressure by the summation of mole fractions, use inverted Antoine equation, then we have bubble B calculation, and notice right now the difference between the summation of y and 1 is 1.7 times 10 minus 5, which means what? It is less than 1 in 10,000. Now we can stop and we can report that the bubble temperature of this system is 300 Kelvin, and the mole fractions of the components in the Weber phase are 0.77 for benzene, 0.175 for toluene, and 0.051 for xylene. Same thing with dew point calculations, other than the initial guess is the same as done in the bubble T calculations, but notice right now it changed. Why did it change? Because the total pressure is different. In the case of bubble T, we have a total pressure of 0.0714. In dew T, the total pressure is 0.02903. So we end up that the boiling temperature for benzene at this pressure is 269, 293 for toluene, and 315 for xylene. And using the weighted average, we can obtain an initial guess of 290.646 Kelvin as an initial guess. Now we have a temperature and we have the y's. We can calculate a dew P calculations, and to calculate the mole fractions in the liquid phase, notice what I'm using, the total pressure, that is the real Weber pressure, not the calculated Weber pressure here. Now what do we have? We have a summation of x's equal to 1.711. What does this signify? It signifies that the temperature is lower than what is necessary. We need to increase the temperature. How do we increase the temperature? Once again, we revert to the key component. The first key component is benzene. Its Weber pressure at this initial temperature is 0.0888. We multiply it by 1.711. What do we get? 0.152 bars. Using the inverted Antoine equation, we can get an estimate for temperature, which 302.11. Calculate the Weber pressure for the components. Calculate once again the summation of x's, and notice right now what do we have? We have a summation of x's less than 1. What does summation of x's less than 1? It signifies that the temperature given is higher than what is required. So we need to scale the new initial guess for temperature. How do we scale it? The total pressure, the Weber pressure of the key component multiplied by the summation of x's, it should yield an initial guess of temperature of 299.557, and right now we have a summation of 1.0248. So what does it signify? The temperature is lower than what is necessary. We need to increase it. Scale the Weber pressure of the component using multiplication with the summation of x's and get this value. Keep on doing this until you get a value less than 1 in 10,000. All we needed is 5 iterations in this case to calculate the bubble T, the dew T, solution for this example. Now, what I'm going to demonstrate right now is using HYSYS, Aspen HYSYS, how to calculate bubble point temperatures, dew point temperatures or pressures, and I'm going to apply it to the same examples that we have here. I'm just waiting for HYSYS to open up. I'm going to start a new case in HYSYS. And if you are not familiar with HYSYS, the first thing that we need to do is to add component lists. And component list, I need to benzene. I can search right now by name of component, benzene, toluene, first one here, and xylene. If you remember your organic chemistry, you have 3 isomers for xylene. I'm going to need the metaxylene isomer. Now, once we are done with the component addition, we need a fluid package. What is a fluid package? A fluid package is nothing but the thermodynamic models to be used for calculations. I'm going to use Antoine, which is equivalent to using Raoult's law. But notice please that the Antoine equation in HYSYS is much more complex than the Antoine equations that we know. It has 6 coefficients rather than 3 as you are used to, which is common in vapor pressure models, so don't worry about it. It's just a minor variation in this case. So I'm done with this. Now, once we are done with this, we can go to the simulation, and this is the model palette. All I need is a stream. And if you know that HYSYS uses color coding. In this case, we have a light blue arrow. Light blue arrow indicates that we don't have enough information. If I double click on the stream, if you notice, we have nothing here. If I want to carry out bubble pressure calculation, I have to assume that temperature is known. What we have known is now is 300 Kelvin for temperature, and I need to add the composition for benzene as 0.4, toluene 0.3, and xylene is 0.3, and this is an OK. Now, if we go to conditions, still HYSYS is telling us we have unknown pressure. I don't want to add pressure. What I need to do really is to look at the vapor phase fraction. What do we know about the vapor phase fraction? If you remember or recall the phase diagrams that we talked about, if you have a bubble point system or a mixture at the bubble point, it means that its liquid fraction is 1 and its vapor fraction is 0. So I'm going to put a 0, and notice now what happened. HYSYS managed to calculate all those calculations. If I go to compositions now, we have 0.6, 0.24, 0.1529. This can be contrasted. .77, 0.175, 0.051. Why is this difference? And if we notice the calculated pressure, kilopascal. No, I'm sorry, I messed things up. Let me go back to conditions. It's not 300 degrees Celsius, it's 300 degrees Kelvin. And this should fix things. In the composition, right now we have 0.77, 0.178, 0.0535, and 0.77, 0.18, 0.052. It's almost the same. The total pressure here using hand calculations or Excel, 0.07145 in HYSYS. What do we have? The total pressure for conditions. It's 7 kilopascal divided by 100. It's 0.07. So if you want to calculate the bubble pressure, all you need to give him HYSYS is the temperature and the composition. If I would like to have a dew point pressure calculation, what I need to do really is just to set the vapor fraction to 1. And notice right now what happened. The total pressure is 2.932 kilopascals. Divide by 100 to obtain the bar, and let us compare it to our dew pressure calculations. It's 0.029 bars, while in HYSYS it is 0.02932. It's almost the same. For the composition in the liquid phase, it's 0.087, 0.21, 0.70. The composition 0.087, 0.21, 0.70, and in Excel, UP, it's 0.084, 0.21, 0.71, almost equivalent values. Now, if you would like to have bubble T or DUT calculation, what you need to set is to give him the pressure and delete the temperature from here. So I'm going to delete the temperature, and this one is deleted also. So if we want a bubble T calculation, I will set the phase fraction to 0, and I will set the pressure to 7.145 kilopascals. And let us see, the temperature almost 27.18, and the composition is almost 178.0536, which is almost the same as that. If I would like to have a DUT calculation, I would set the vapor phase fraction to 1, and in this case, and the pressure, 2.92332. Notice the temperature 2685, and same thing for composition, we got the same compositions. So this is a conclusion of calculations using HYSYS and Excel, and I hope that you will be ready for the next lecture, which is concerned about dealing with flash calculations, which is one of the most important topics in chemical engineering, because it's the introductory part to distillation calculations in your mass transfer operations course. Thank you for your attention.